Amid the scorching plains of South Asia, where drought has shaped life for centuries, Pakistan set out to challenge one of nature's harshest limits. Engineers began carving a massive man-made irrigation canal, designed to divert the mighty Indus River deep into some of the country's driest desert regions. But moving a river across barren land meant battling unstable soil, extreme heat, and the unforgiving physics of flowing water. So how do you force life through a landscape where nature never intended it? This is the story of one of Pakistan's most critical water megaprojects. For decades, southwestern Pakistan was defined by severe water scarcity. Vast plains lay dry and cracked, rainfall was brief and unpredictable, and extreme heat made agriculture nearly impossible across much of the region. Yet, just beyond these parched landscapes flowed the Indus River, one of South Asia's mightiest water systems, while local communities still queued daily for every drop of clean water. This stark contrast sparked a bold national decision to redirect the river inland, across arid terrain, and into regions long starved of water. The Kachi Canal project, stretching approximately 499 kilometers, began in 2002 with intermittent construction and was substantially completed more than 2 decades later. With an estimated investment exceeding $800 million, the project employed over 10,000 workers and hundreds of modern machines operating continuously in some of the country's most challenging terrain. With planning complete, the first steps moved into action. Hundreds of excavators and massive dump trucks launched one of the largest digging operations ever attempted in the region. Each day, nearly 70,000 tons of sand and soil were removed from the desert along a construction corridor stretching almost 250 miles. More than 1,200 engineers, operators, and laborers worked in rotating shifts, enduring daytime temperatures that frequently soared above 115 degrees Fahrenheit. The canal was carved into a wide U-shaped profile, approximately 150 feet across at the base and averaging 23 feet deep, allowing water to flow naturally without pumps. To achieve this, the longitudinal slope was controlled within an astonishing margin of just 1 inch per 100 feet. Survey teams rechecked elevations every 160 feet using laser leveling instruments to maintain perfect alignment. Most of the excavated sand was reused to build embankments on both sides, forming levees 10 to 16 feet high. In hilly terrain, bulldozers cut through layers step by step, while in low-lying areas, the challenges only intensified. Truck convoys hauled and stabilized fill material until precise grade levels were achieved. In zones with weak soil, engineers drilled 16-inch sand piles reaching depths of 20 to 25 feet, or reinforced the base by mixing cement and clay to prevent long-term subsidence. The construction zone stretched for hundreds of miles, dotted with concrete batching plants, mechanical workshops, and field engineer camps. Beneath the scorching sun and swirling desert dust, endless lines of trucks and machines moved like a mechanical river, carving the path of a real one into the heart of the desert. This excavation phase lasted for months, but in the Negev, the challenge wasn't just heat or dryness. It was the thirst of the sand itself, capable of absorbing exposed water within hours. If the canal bed wasn't properly sealed, the water would simply vanish. That made the lining phase one of the most critical stages of the entire project. First, the canal bed and side slopes were moistened and leveled with a 2-inch layer of fine sand. Then concrete panels, 4 to 5 inches thick, were poured in sections measuring 16 feet by 10 feet. Expansion joints separated each slab, filled with hot bituminous sealant to prevent seepage while allowing thermal movement. In areas with unstable subsoil, additional reinforcement ensured the canal could endure decades of continuous flow. Beneath the concrete lining, an additional HDPE geomembrane layer was installed, anchored with steel fixings and protected by a cushioning layer of sand. In total, more than 220 miles of the canal were fully lined, creating one of the largest continuous waterproofing systems ever constructed in the region. Along the embankments, engineers planted vetiver grass and desert acacia to stabilize slopes and reduce drifting sand. From the air, the canal appears as a shimmering silver ribbon slicing through a sea of gold, a concrete artery waiting to deliver its first life-giving water into the desert. But a canal of this scale is far more than a simple trench. It requires hundreds of auxiliary structures to manage flow, protect against floods, and ensure safe transportation. At the head of the system, engineers from WAPTA constructed the head regulator at Tansa Barrage, where water from the Indus River is diverted into the canal through 9 massive steel gates. Along its length, more than 900 engineered structures support the system, including reinforced concrete bridges, spillways, siphons, drainage culverts, and aqueducts carrying water across natural streams. Wherever the canal intersects a road or railway, new bridges were built to maintain uninterrupted traffic. Even where the canal crosses active waterways, cross-drainage structures were installed along the route, massive conduits designed to allow natural waterways to pass beneath the artificial canal without interruption. In addition, distribution gates were placed every 6 to 9 miles to regulate water flow into secondary branches. Every component had to operate in perfect harmony, because a single malfunction, whether at a gate, siphon, or aqueduct, could cut off water to hundreds of hectares of farmland downstream. After more than 15 years of construction, the canal finally entered its water testing phase. Engineers slowly opened the gates at the Tansa Barrage, allowing Indus River water to flow section by section. Discharge was increased gradually from 500 to 2,000 and eventually 6,000 cusecs, while technical teams inspected every segment. Pressure was measured, leaks were checked, slopes were monitored, and even the smallest ground movements were recorded. Every deviation was corrected before full operation began. When the first surge of water rushed through the once cracked, lifeless canal bed, the districts of Dera Bugdi and Jal Magsi erupted in celebration. Locals called it the day the desert came back to life. Wherever the water flowed, cheers followed, because this wasn't just water. It was hope, survival, and a future restored. It was a flow of hope, the fulfillment of a dream generations of farmers had waited their entire lives to see. When the first drops of water finally reached the arid land, everything began to change. Not just on the surface, but deep within the lives of the people. Fields that once cracked under the burning sun started to flourish again. Farmers who had abandoned the desert returned, pitching tents, driving stakes, and plowing the first crops amid sand and rock. Water from the main channel of the national water carrier was carefully divided through a network of secondary canals, pressure pipes, and drip irrigation systems. Technology pioneered in Israel to conserve every drop of water, as precious as gold. The project, which began in 1953 and took over 11 years to complete at a cost of 420 million Israeli lira, equivalent to hundreds of millions of dollars, once operational could transport up to 72,000 cubic meters of water per hour. Fresh water now flowed from the north all the way to the Negev, transforming once hopeless regions into thriving agricultural zones and giving life back to the desert that in the early years. Tens of thousands of acres of farmland turned lush green. Where once there was only dust and sun, now stood orchards of oranges, vineyards, wheat fields, vegetable farms, and rows of date palms heavy with fruit. From satellites, a long green ribbon winds across the golden desert, the artificial lifeline connecting Israel's north and south. Villages were rebuilt, children had schools, and high-tech farms rose from the sand. Continuing our journey, let's explore another remarkable water supply project in Asia. This time, instead of drawing from rivers, engineers are channeling water directly from the sea through a massive network of steel pipelines, bringing life to one of the harshest deserts on Earth. The process begins by drawing seawater from the open ocean and transporting it inland, establishing a steady, uninterrupted supply for the desalination facility. Large intake lines are carefully positioned offshore, with installation crews aligning each segment before lowering it into place using heavy lift cranes on barges or coastal platforms. As the pipeline extends toward the shore, individual sections are joined sequentially, forming a continuous conduit designed to withstand constant hydraulic pressure. Precision alignment is critical, as even small deviations can reduce long-term performance and flow efficiency. Once installed, the intake line is reinforced with structural support frames, ensuring stability and durability for decades of operation. The pipeline is securely anchored to the seabed, but its journey begins long before reaching the water. Large staging yards along the route store fully manufactured steel pipe sections, grouped by diameter, length, and installation sequence. Engineering teams conduct final inspections, checking straightness, coding, and identification markings. Proper organization here is essential to maintain continuous workflow, minimize delays, and reduce errors in the harsh desert environment. Meanwhile, survey teams establish the precise pipeline route using GPS, total stations, and terrain data. The alignment is marked on the ground with stakes and visible paint, ensuring the pipeline follows the most stable and efficient path, avoiding weak soils, shifting sands, and erosion-prone areas. For pipelines stretching hundreds of kilometers, this accurate routing is critical to long-term structural integrity. Before trenching begins, the construction site is carefully cleared and leveled, preparing the way for installation. To allow heavy machinery to operate efficiently, temporary access roads are constructed parallel to the pipeline, accommodating trucks, excavators, welders, and material transport vehicles in the desert. Site preparation also includes dust control and sand stabilization measures to maintain visibility and worker safety, critical steps for ensuring smooth progress throughout the project. Once the route is finalized, large tracked excavators begin digging the trench along the marked alignment. Trenches are excavated to precise widths and depths, providing enough space for pipe placement and backfilling. Excavated soil is sorted on site. Suitable material is reserved for backfill, while unsuitable soil is removed. Maintaining consistent trench depth and alignment is vital to prevent pipe deformation or misalignment after installation. In sections crossing steep or rugged terrain, explosives are carefully used to carve trenches directly into solid rock. Controlled charges are placed and detonated in sequence, fracturing the bedrock and preparing the foundation for the pipeline. Along the planned alignment, blasted trenches create sufficient depth and width to securely seat the pipeline, even in areas where mechanical excavation is impossible. This method allows construction to continue through extreme landscapes while keeping the pipeline buried, protected, and structurally stable. After excavation, the pipe is never placed directly on the trench floor. A layer of carefully selected material, typically fine sand or screened soil, is spread evenly along the bottom to form a bedding layer. This layer distributes loads uniformly, reduces stress concentrations, and is leveled and lightly compacted to achieve the precise elevation. In desert terrain with loose, dry soils, this step is critical for long-term stability. For large-diameter pipeline routes, a construction corridor approximately 40 meters wide is prepared in advance, allowing continuous installation at an average pace of 1.5 kilometers per day. Pipe sections, roughly 18 meters long, are chosen to minimize field welds, while imposing exacting demands on alignment and handling. During lifting, transportation, and precise alignment, each pipe joint is carefully prepared. At the welding site, a hydraulic internal lineup clamp is inserted into the joint and expanded with 360-degree gripping shoes to hold the two sections perfectly concentric and aligned during the root pass. An automated welding operation, supported by roughly 80 personnel and dozens of specialized machines, can complete up to 150 welds per day on 42-inch diameter pipes. After welding, every joint undergoes automated ultrasonic inspection to ensure it is free of internal defects. Field joint coating crews then abrasive blast the surface and apply a multi-component liquid epoxy coating, creating a durable, fully sealed protective layer. The assembled pipes are then lowered into the trench using side crane tractors and specialized tracked vehicles, with multiple side booms operating in sequence to handle the large diameter pipeline efficiently and safely. Each section of the pipe string is lifted using padded slings and steel cables to protect the coating, raised evenly, and held suspended above the ground as the machines move slowly along the trench. Precise coordination between operators is essential to prevent twisting, bending, or contact with the trench walls. Once perfectly aligned, the pipe is lowered gradually, centimeter by centimeter, until it rests securely at the center of the trench on the prepared bedding. Surveyors continuously monitor elevation, straightness, and natural curvature to ensure no residual stress is introduced. This method allows fast, controlled, and highly accurate placement, ideal for long, straight pipeline routes across flat desert terrain. After placement, the trench is backfilled in multiple layers. The initial layer uses fine material to protect the pipe coating, followed by previously excavated soil. Each layer is mechanically compacted to the required density, minimizing future settlement. In desert conditions, where wind and temperature extremes can compromise soil structure, proper compaction is critical to the pipeline's longevity. But where does this pipeline get its water from? The pipeline draws from a nearly inexhaustible source, seawater. But seawater contains about 3.5% salt, too salty to drink or use for irrigation. That's why desalination technology was developed, giving Saudi Arabia a virtually unlimited supply of usable water. The pipeline carries water from massive desalination plants along the Red Sea, each capable of converting 7 million liters of seawater into drinking water daily, a process that consumes enormous amounts of energy. Once treated, the water is delivered through a modern pipeline network to homes and farms across the kingdom. The cost is high, around $5 per cubic meter, compared with just a few tens of cents per cubic meter in countries like the United States. So far, we've explored 2 massive water diversion projects in Asia. Would you like to discover similar engineering marvels in other countries? Share your thoughts in the comments below. Thanks for watching, and we'll see you in the next video.